Good afternoon. I'm Dr. Underdown. This is my third video that I am making. My son, who's a mechanical engineer, and I were having a conversation the other day about Maxwell's equation. So I thought I would make this video for the benefit of everyone about what Maxwell's equations are and why we need them. And I'm also a professor, and so I put it in a format that I normally do for my students when I'm lecturing. I put the information inside a Jupyter notebook. So this lecture is entitled Maxwell's Equations Made Simple, and we're going to start discussing the equations, and then we'll talk about fields, and then we will work into a finite difference time domain simulation. So, what is the ideal? Maxwell's equations are not just four abstract equations. These equations explain how electric charges, both positive and negative, can create electric fields. They talk about how current, which is flowing through a wire or even in a field, can create magnetic fields. They talk about how changing magnetic fields can create electric fields, how changing electric fields can create magnetic fields, and then they also explain the propagation of electromagnetic wave through space. The physics behind these equations explain how antennas, waveguides, radar, microwave circuits, EMC, optics, wireless communications, and finite difference time domain simulation works. We owe this understanding of these equations to the person who takes the name of those equations, and that is James Clerk Maxwell, who we see a picture here. And what is important about Maxwell, before he came along and summarized these equations here, scientists used to think that magnetic fields, electric fields, and everything were all separate entities. But Maxwell came along with these four equations, and he was able to unify electricity, magnetism, and light. And then after Maxwell, light could also then be explained as an electromagnetic wave. So here are the four Maxwell's equations here. We're going to go through here. We're going to name these equations, and we're going to see the importance of them. Equation 1 here is called Gauss' law for electricity. You can see here that it's del dot E is equal to the charge density over epsilon naught. The equation itself is not important, but the meaning behind it is. What it shows here is that electric charges are sources of electric fields here. So I show here two different electric charges here. I have a positive charges. Positive charges are sources of electric fields. So you can see that I have these arrows going away from this electric charge, showing that it is sending out a field away from the charge here. Now, negative charges like electrons, these are sinks for electric fields. So you can see that I have my field lines in here then coming in from infinity toward this negative electric charge here. So this is Gauss' law for electricity. Then we have Gauss' law for magnetism. Del dot B is equal to 0. What does this equation mean? This equation means that there are no magnetic monopoles. We have an example of a bar magnet here. We can see the field on this bar magnet. These field lines, they make closed loops. Field lines, they come out of the north end of the magnet and they come into the south end of the magnet. Now if I take a saw and I cut down the middle here between north and south, I don't get a separate north pole, or I don't get a separate south pole. I just get a smaller magnet, and each of those smaller pieces will have north and south poles. And this is what this law here is saying. But not only do we have the law here, but I want you to see here that the field lines here that are around a magnet. They're different from electric charges with active source and sinks. Here, the field lines here, they perform loops out of the north and into the south of the bar magnet. Now, equation 3 is called Faraday's law. And so Faraday's law basically says that if I have a changing, so we have del B here, del over del T. I mean, not del, but if we have this derivative, this is a partial derivative of B with respect to T here, then it's going to end up causing the curl of an electric field. So a changing magnetic field here then produces changing electric field here. Why is this important? This is the physics behind how generators and transformers and inductors and wireless power transfer and coils and check and changing magnetic flux works. I wanted to show you an example here. So I have this demonstration here. I have a bar magnet. So you can see that I have a bar magnet here which I can move around. And here are the field lines of coming off of this bar magnet here. And there is a compass here that you can see that are interacting with these field lines. And you can see that these fields come out of the north, they go around, and then they come back into the south. Now we go to the next demonstration here. So now not only do I have my bar magnet, I have a couple of loops of wire which are connected to the light bulb. And so now as I move this magnet toward the coil here, it causes electrons to flow in the wires, and you can see it lights the light bulb. And if I come back the opposite way, it does the same thing. And we can see how the field of the magnet is changing too as I move this magnet back and forth. Now the third demonstration here shows a battery here that is producing electric current inside this field here, and you can see I have a compass here, and you can see that as I move this compass around, it is interacting here with the field of that is generated by this coil. So in other words, this coil itself is acting like an electric magnet. Now here are transformers. Transformers are basically made up of two different coils. You can see here that I have a primary coil here which I connected it to a power source, and then I have a secondary coil over here which is connected to this load, which is a light bulb here. Now if I get some movement between this coil here and this secondary coil, energy is being transferred from this primary coil here to the secondary coil, which is then causing this light bulb to light. And I think the last one over here basically shows that if I turn this magnet around by letting it this paddle wheel turn under the force of water here, then this is generating a changing magnetic field. That changing magnetic field is cutting across this coil, coupling to it, and it is causing current to flow first in one direction, then the other direction in this coil, and it's causing the light to light. And you can also see that my compass is responding to this changing field. So I thought this would be a good way to demonstrate then here Faraday's law. Now equation 4 is called Maxwell law, and we can see here that I have a changing electric field. I have some constants here. I have a current density here, J, and that this either a current or a changing electric field is going to produce a magnetic field. And the second term here was a term that Maxwell added, and it was very key because this term here allows electromagnetic waves to exist in free space. Now finally, I want to talk about what is called the current carrying of a wire. I'm going to have a straight wire, and I'm going to talk about the right hand rule. I was looking for an image of that. I could not find an image, so here is some code written that will generate a picture of a current carrying wire in the magnetic field around here. So this wire is pointing out of the screen. So if you take your right hand and you point your thumb in the direction of positive charge carriers flowing out, your fingers wrap around the wire, and the directions your fingers point is the direction of that magnetic field that is generated around the current carrying wire. Now we want to go then from Maxwell's equations to waves. So we're going to first assume that we are in free space. So in free space, there is no charge density and there is no current densities. Based on Maxwell's equation, I can propagate an electromagnetic wave, for example, a light wave or a radio wave through free space. We can see here that I have an axis in here that helps us to picture this propagation of this wave. I have the y-axis here, and you see that my electric field is going up and down in this plane, going positive and then on a negative peak and back, and then perpendicular to that in the z direction here I have my magnetic field that is being created, and it is also staying lockstep with the electric field. And then this wave here is a traveling wave, and it's actually traveling in the x direction. So when a transmitter sends out an electric wave from an antenna, this type of wave propagates from that antenna, and then say a broadcast antenna at a radio station, and then another antenna at your home on your radio will pick up that wave, and then it will dissect that wave to get the information out of it that it's carrying, and we're able to hear music. Or the same type of thing happens from the sun, that the sun is sending out particles or waves depending on how we want to look at it, and that kind of gets into quantum mechanics. But the sun is a source of electric waves, light, and that light is propagating similar to this as an electromagnetic wave from the sun to the earth and brings warmth to us. There are some, I'll just pause for a second here. There are some other videos and that I'm not going to get into right now, but I'll leave them here so you can see them, and maybe you want to look at them later. So now we want to go from the theory to numerical simulation. Now in my first video, I showed you the code that I wrote to generate a simple Gaussian pulse that was then radiating in one dimension, so it was sending out pulses to the left and to the right, going off into infinity. And we want to be able to simulate that. Well, we cannot use Maxwell's equations directly as written because these are continuous equations, and so continuous equations generate an infinite number of points, and no computer, no matter how big it is, has enough memory and resources to be able to simulate an infinite number of points. So what we do is we take our wave and we break it up into small little slices and in time and space, and then we step through our equation and we look at selected points on that wave, and then that is what we simulate on the computer. So as I brought out here, computers cannot solve a continuous field directly, so we divide space and time into small steps. That is the central idea behind the finite difference time method. So from this word here, finite difference means we approximate the derivative using nearby samples, and time domain means we step that field forward in time. And then we use the code that we write using update equations to update the electric and magnetic field as it marches across our simulation domain. I also mentioned in that first video about the Yee Grid, and because these fields generate each other, electric field generates the magnetic field generates the electric field. Here I'm showing some simulation area here, a one-dimensional problem here, and this is and I'm showing that I have an electric field right here at this grid point is equal to 0, and then I show a magnetic field at this grid point space half a grid away, and then I have another electric field, and then I have another magnetic field, an electric field. So just as they generate themselves as they're propagating in space or through some device, when we code this, we have to code it the same way that we have electric field, magnetic field, electric field, magnetic field, and so on. So what is this picture telling us? We can see in this picture that the magnetic field is then used to update the electric field, and then the electric field is used to update the magnetic field, and this just repeats across the simulation domain, and a wave then will propagate through our simulation grid. Now this is the code that I showed you in my first video. The only difference in this code here is that the way I have it written here, I'm going to take a snapshot in time. So here is my simulation domain. Remember that I said it was 400 points long here, so I have 400 grid points, and that I was starting a wave here at the source point at grid point number 100, and you can see that what it is doing, it is generating two waves, one traveling to the left and one traveling to the right. Now ideally these pulses just continue off into infinity, but as we saw in that first video, I was having some trouble with the code, and actually what it was doing, it was these pulses were coming over here to the left edge and to the right edge, and it was like a tennis ball hitting off the wall, and then they were bouncing back into simulation space. Now they are not supposed to do that because that doesn't represent the true physics, and so then I worked on the second video to reduce that pulse. And then here is some code that shows you that simulation, so I'm going to just bring it back here to this end, and then I'll let it play, and then I'll just step through it. So I'm going to have a source point here at grid point 100, and we're going to see that pulse grow, and then it's going to travel to the left and to the right. Now you can see this is the reflections that are coming there, so I'm going to stop this, and then I'm going to basically step my way through here. So you can see here that the pulse is building, and then you can see that the pulse is traveling to the left and to the right. Ideally that pulse on the left there should just disappear and go off to infinity. Unfortunately, this is like the first code that I wrote. It is reflecting off of that. Well, I guess it's similar to the second code because it's reduced some. It's reflecting off of that left wall boundary and then coming back in the simulation space. And if I keep stepping through this, you will see that the right pulse is going to do it again. Not as bad as it was in the first simulation, but it's still not totally gotten rid of. So we'll have to work on that. Okay. So, as I said, what does this simulation shows? It shows the pulses generating here at this grid point 100, traveling one to the left, one to the right. I do have some absorbing boundary conditions there, so it has reduced the size of that reflection back into the simulation space, but not totally. So, what is the connection of all of this to engineering? These same Maxwell's equations show up in practical engineering problems, whether we're talking about antennas or radar or waveguides or microwave circuits or shielding or an EMC or EMI problem or grounding and bonding, again thinking about EMI types of problems, caving and cables and harness couplings. So again, we're talking about E&I problems. Enclosure resonances, this all deals with EMI problems. Connected parasitics, that's EMI problems. And then now we go into optical systems and wireless transmission of energy. So these then equations help us to model and to simulate all of these different systems, all using Maxwell's equations. Why are simulations important? A good electromagnetic model and simulation helps us to answer questions like, where is the coupling path? If we're doing some type of troubleshooting, is the issue radiation, conduction, grounding, bonding, shielding, or resonance? Which geometry or which material matters the most in this particular design? Or can we reduce the test cycle by building our models virtually first before we actually do a physical build of a prototype? So the goal then is not just to make some type of pretty plot. The goal is to connect a system level symptom to physical mechanism. So in closing, Maxwell's equations tell us how electric and magnetic fields behave. The finite difference time domain turns these equations into step-by-step updating equations or a numerical procedure that then we can then plot, march across our simulation domain and then look at plots of how that field is and energy is traveling through that simulation space. And so this then is the bridge from physics, from the equations that we saw, Maxwell's equations, to the simulation. So as we see here, we start out with Maxwell's equations. We turn those into algebraic, these are differential equations. We turn them into algebraic equations as finite differences. Then we use updating equations to update the field as they are marching across our simulation space, and then by examining the results that they get, they give us engineering insights. So I want to thank you for listening, and I will see you next time.